Just, just, just interrupt at any point, okay? Okay, good. So I'm going to tell you about work I did, as you see, over the past years. So we had some enthusiasm 7, 8 years ago, and then we learned some new things, and then I've started writing new papers on this. So I'll try to summarize the whole story. Uh, the motivation, sorry, all of this was done in work with with these amazing people that are currently affiliated with institutions in these cities. Okay, so the motivation here is kind of simple. As you all know, there's this thing called ADS CFT, which is a framework or a method to understand, on one hand, strongly interacting quantum field theories, and on the other hand, quantum gravity, at least in asymptotically anti-de Sitter space. And very kind of obnoxiously, it can be summarized in one equation, which is that the CFT path integral, the partition function in the presence of some background sources, J, should be in some sense equivalent to string or M theory on this asymptotically anti-de Sitter space with some specific boundary conditions for some background fields phi. And and of course, we would like to kind of extend this idea or this correspondence to things that are not asymptotically anti-de Sitter space. And on the dual QFT side, this would mean that I don't really have a strongly interacting CFT. So I have some kind of a non-conformal theory that I'm studying. And how to do this is not very clear. But I think it's an important thing to understand. And the goal of the talk is to explain at least one instance where we can do something like this. Okay. Why should you care? Well, if you are ki- kind of holography oriented, you should probably care and you would like to extend, as I said, ADS CFT to non-conformal settings, non-ADS asymptotics, and so on. So these are these first two points. And I want to emphasize that we would like to do this not just spiritually in some sense in words or schematically, but we would like precision tools to compute on the two sides of the correspondence and get some kind of confidence that we're doing the right thing. If you're a stringy person, you may just ask, well, I want to understand D-branes and not only D3-branes, but general Dp-branes with curved word volumes in string or M theory, as well as their low energy supergravity approximation. And so then again, this connects somehow to the question I'm asking. And if you are a pure QFT person, well, these non-conformal theories are usually some non-abelian Yang-Mills theories at strong values of the coupling. And of course, we would like some tools to compute correlation functions or scattering amplitudes, if you wish, in such non-conformal theories. And so the goal of the talk is to kind of connect all of these four bullet points into one story and try to convince you that we have understood at least bits and pieces of this broader program. Okay? Good. And to kind of quickly explain what will be the setup, we can go back to this relatively famous paper from 98 that I've listed here by Itzakin, Maldacena, Sonnenschein, and Yankelovich, where they, very soon after Maldacena's paper on ADS5S5 and D3-branes, they kind of pointed out that the story should go through for all other Dp-branes, at least for p less than or equal to 6. So during the talk, p will be the number of spatial directions on the D-brane, and of course it should be really an integer, but I will treat it often as a parameter, so I'll keep it arbitrary, p. Okay? So on the world volume of the Dp-branes, on one hand, we have open strings that end on the D-brane, and at low energies, the open strings should describe maximally supersymmetric Yang-Mills theory on flat space, on the world volume of the brane, which at the moment I assume it's just flat space. On the other hand, Dp-branes are heavy objects. They curve the space-time. And so from the point of view of the closed strings, then I have some curved supergravity solution in which I can take a near horizon limit, and then I find what is listed here on the slide. So I find a very simple metric. So I have the flat, the thing in red here is the flat world volume of the brane. There's a radial coordinate u here, and there's some internal sphere, omega 8 minus p dimensional sphere. And then if p is not equal to 3, so if you don't have Dp-branes, but any of the other branes, the dilaton field phi actually changes with scale. And so you have a running dilaton, as it's called. And then the Ramon-Ramon form takes a very simple form, like here. And so as you see here, I have some kind of a non-ADS background. It's only for p equals to 3 that this whole thing collapses to ADS5S5. And so I need to learn how to talk about this solution. And it's kind of not so hard to convince yourself that actually the supergravity approximation breaks down for very large values of u and for very small values of u. So I have an infrared and a UV cutoff in this background, if you wish. So the dilaton goes very large or very small, and then curvature also have to be controlled. And analyzing this, I get a bound or a regime in which I can actually trust supergravity, okay? Okay, this was all explained in this paper. And then another thing that you quickly learn is that if you try to study the thermal version of these backgrounds, something like a Schwarzschild solution, which is known, then you learn something interesting about the on-shell action and the free energy. And this goes by a funny name called scaling similarity. So ADS5S5 has conformal invariance on the ADS side. This is lost now. However, you still have something like scale covariance. So the on-shell action transforms in a very special way under scaling of the coordinate u, or alternatively shifts of the dilaton. And this means that the on-shell action is going to scale in this way with n. And if you wish, the thermal free energy is going to scale with this funny power of the temperature. Okay? So maybe this is the physically most interesting thing or easiest to explain. If you put p equals to 3, you are in a 4-dimensional quantum field theory, which is conformal, and you find t to the power 4. This is the familiar Stefan Boltzmann law for the emission of photons at finite value of t, simply because electromagnetism is a massless theory, so you do get a power of 4. But in every other dimension, the power seems to be funny. So this funny fractional powers are due to the fact that the theory, the underlying Yang-Mills theory, is somehow strongly coupled. And we don't know how to compute these funny powers of t or these funny powers of the coupling purely from the QFT side. So even arguing that the free energy has to scale with this fractional power is impossible, as far as I know, from pure QFT analysis. I should say here that for low values of p, our lattice friends, so people who do lattice quantum field theory, have studied these kind of Yang-Mills theories. These are maximally supersymmetric, very special theories. And for low values of p, they can actually study the thermal free energy and within some accuracy find exactly this scaling behavior here. But the goal of the talk here will be to kind of understand how things work at 0 temperature. So insist on keeping supersymmetry. Of course, if I heat up Yang-Mills, I'm going to break supersymmetry. So I want to keep supersymmetry, be at t equals 0, and then try to find a situation where these approximate signs or these scaling signs are now equal signs, meaning that I would like to explicitly compute both the scaling with n and with the Yang-Mills, but also the coefficient. Okay, so this is one way to motivate what I'm trying to do for at least half of the talk. Okay, any questions so far before I move on?
Nikolay, I'm going to ask you some very naive question.
Sure,
Maybe
sure.
it help
Yes,
everybody.
please.
So, is it so immediate that at finite temperature you definitely break supersymmetry? I mean, conformality for sure, but
Yeah, very good. People call many things finite temperature, but what I meant here is just the usual thing of taking something like a Schwarzschild black hole and inserting it here. I didn't write the metric explicitly, but that solution of supergravity will break supersymmetry, and this is what I call the thermal free energy. So this, if you wish, is the scaling of the on-shell action of non-conformal Schwarzschild. Now, if you go to the QFT side and you ask, oh, what if I put a QFT on a circle? Can I specify boundary conditions that keep supersymmetry? Indeed, this could be done, and it's called the index or the Witten index or the superconformal index or something. And those things are more, well, they're different supergravity solutions, which I don't think have been studied in this specific setup. So here I mean something very, very simple, just the thermal Schwarzschild background. Yeah.
thanks.
Yeah, good. Okay, so what's going to happen during the talk? I'll try to convince you that if we are aiming to keep equal signs, keep as much supersymmetry as possible, meaning 16 supercharges, and keep things computable, one way to do all of this is to put the super Yang-Mills theory on the round sphere. And I will show you how to do this. Then the reason this is nice is that you can actually compute the path integral or the free energy of this model, because one can use supersymmetric localization to reduce the path integral to a matrix integral and then analyze that matrix integral in terms of the usual large N tools that we have. So this will be a large N analysis. And then using that, I will show how to compute the free energy, meaning a logarithm of the path integral. I'll call this the free energy, just log of z, as well as a certain insertion of a line operator, a Wilson line, on the equator of the sphere. And these two things I can compute at large N using these matrix model tools. And then I'm going to move to the bulk side, and I'm going to show you. So now I have super Yang-Mills on a sphere, not on flat space. So the backgrounds that I showed you here have to be modified accordingly, right? I don't have a conformal theory. I'm putting a theory on some other space that is not flat. I'm going to turn on couplings and different sources. So on the gravity side, I need to construct new backgrounds of supergravity, which we call spherical Dp-brane solutions. So I'm going to show you how to construct those. And then to connect these two aspects of the story, I have to do holographic evaluation of the on-shell action of these Dp-brane solutions, and then compare with the free energy computed on the QFT side. And so when all of this is done, you'll see that we find a non-trivial agreement between supergravity and quantum field theory without anywhere having anti-de Sitter space or anti-de Sitter asymptotics or conformal invariance. And at the end of the talk, if I have time, I will tell you something more recent, which applies to these flat Dp-branes, so the Young-Mills on a flat space, you could ask independent questions about computing correlation functions in this model and how to do this from the bulk supergravity side. And we've learned how to do these things, and I will try to explain how to compute these Witten diagrams in these non-ADS spaces. Okay, so this will be the plan of the talk. And as I said, you should interrupt me at any point if you have questions. Good. So this is what's going to happen. I will first tell you about super Young-Mills on a sphere. Then I'm going to move to the supergravity side and show you schematically how to construct the dual supergravity solutions. And then to convince you that these two things are actually dual to each other, I will try to compute things and match them independently from the two sides. And finally, I'm going to tell you about these correlation functions. Okay, maximal super Young-Mills on a sphere. This I should emphasize that this was understood very nicely in a paper by Matthias Blau that is preceding the famous Pestun and Festuccia-Seiberg papers. So I just want to emphasize this. Okay, so here is an explicit Lagrangian in Euclidean signature of what I claim to be super Young-Mills on the round sphere. So I don't have a notion of time. I don't have a circle. I just have the round empty sphere of radius r. So this funny r here is the radius of the sphere. D is the dimension of the sphere, and it's equal to p plus 1. Okay, so I've written things in this way. Those of you who are old enough to remember how Young-Mills in flat space can be written universally as some kind of a reduction of n equals 1 Young-Mills in 10 dimensions. Well, I'm doing kind of the same thing here. So the first two terms will just give you the maximally supersymmetric Young-Mills in flat space. After appropriately writing things out and taking care of indices and so on. And these extra three terms that have 1 over r or 1 over r squared are needed to keep supersymmetry on the sphere, right? So on the sphere, my spinors are not the same as on flat space, obviously. And so the superalgebra changes, and the Lagrangian has to be appropriately modified to keep supersymmetry. Okay? I'm not going to go into the details of all of this, but it's important to understand that there's these extra terms. Also, it's important that when d is equal to 4, two of these terms are gone. So d equals to 4 will be n equals 4 super Young-Mills in 4 dimensions. And there you only find this one term that has d minus 2 in it. And this term needs to be there with the correct d minus 2 over r square. So 2 over r square, because n equals 4 is a conformal theory. And when you put it on a curved space, on a conformally flat space, you induce a conformal coupling for the scalars of n equals 4. Okay? Good. So this is the Lagrangian of the theory. And as I said, you have these extra terms, 1 over r and 1 over r square, and they break the R symmetry of the theory. So usually I have this SO. So here I'm keeping non-compact R symmetry for some. I've chosen some reality conditions. I'm not going into the details, but if you don't like these non-compact algebras, you can think of this as SO 10 minus 9. That's the R symmetry in flat space, but that's broken to a subgroup like this. Importantly, out of these ingredients, so G Young-Mills is now dimension full. If D is not equal to 4, G Young-Mills has units, but I also have a dimension full scale, the radius of the sphere. And so out of these two things, and n, I can define what's called the 't Hooft coupling, lambda. I call it lambda QFT because we'll have a version of this lambda also on the gravity side, and I want to kind of be careful about conventions. So this is the Toft coupling. And to understand the dynamics of the theory, one should be very careful. So when D is less than 4, the theory is asymptotically free. So at high energies, you're going to get a free theories. High energies means that you don't see really the radius of the sphere because the sphere looks the same as flat space. And so you just get a free Yang-Mills theory in the UV and something strongly coupled in the IR. But importantly, because I'm on the sphere, I have a scale of the sphere. So when I say IR, I really mean up to 1 over the radius of the sphere, right? I have an infrared cutoff set by the radius of the sphere. So I cannot really go to 0 energies. I can only go to 1 over R energies. And that's important. So one way to think of what I'm doing is that I'm doing a covariant supersymmetric infrared cutoff, which is putting the theory on the sphere. When D is equal to 4, I, of course, have conformal invariance, n equals 4 Yang-Mills. And when D is more than 4, the Lagrangian is not renormalizable. So the coupling is going to grow strong as I go into the UV. And I have to tell you what's the UV completion of these models. So if you are a pure QFT person, you should probably not think about this too much and just ignore these models. But of course, we are better than that. We know string theory. And so the conjecture for which there's a bunch of evidence is that for D more than 4, these examples are UV completed in some strange ways. So when D is equal to 5, the UV completion of the Yang-Mills theory is in terms of a 6D CFT, the 2,0 6D CFT. When D is equal to 6, the claim is that you UV complete with something which is not a local QFT. It's called little string theory. And when D is equal to 7, well, the claim is that the UV completion is the full type 2A open string theory. Okay? And just a comment, the Lagrangian that you see on the slide, when D is equal to 1, is exactly the same, although we didn't know it at the time when we were studying this, but it happens to be exactly the same as the what's called the BMN, Berenstein, Modasen, Anastase, deformation of the BFSS matrix quantum mechanics on S1. So D equals 1 is D0-branes, and BMN found a 16 supercharge deformation of the Lagrangian of BFSS, and it is exactly what is written on the slide here. Okay, good. So I
Oh,
have,
hi,
yes,
Nikolay.
yes, hi, hi,
This is Yi. Yeah. Hi,
yes,
nice to see
hi,
you.
good
I
to see
have
you.
a naive question.
Yes,
In the
please.
Lagrangian, there's a psi bar gamma 0 to 1, 2 psi. What singles out 0 to 1, 2 direction here?
Very good. I mean, at some point I have to choose conventions.
Okay.
Yeah, but so that has not much meaning of the ordering of things, 1, 2, 0, 1, 2, and so on. But what is important is that you have to break the global symmetry like this. By
Oh,
the
I
way, I'm
see.
using my pointer to point. Do you see my pointer?
Yes.
Okay, good. So if you are on flat space, the R symmetry group is SO10 minus D. But if you're on curved space, the SUSY algebra changes to SU2 times SO7 minus D.
Mm-hmm.
And
I
so
see.
this SU2 selects 3 directions in the space of scalars, if you wish. And that's what chooses this phi 0, phi 1, phi 2 term.
Okay, thank you.
Okay? Yes. So the way that this works is very interesting, and this was understood by Blau. The supersymmetry algebra in D dimensions on a sphere is the superconformal algebra in D minus 1 dimension in flat space.
Mm-hmm.
And so that's why you have this uh, breaking pattern, if you wish.
Mm-hmm. Okay,
Yeah.
thank you.
Okay. So the SUSY algebra is completely different. The generators are now not the usual constant spinners, of course, they're conformal killing spinners on the sphere and so on. Yes. Good. Now I have a Lagrangian and smart people have shown that you can apply to this action, you can apply the SUSY localization program. I'm not explaining this, I'm just saying that people have shown that the path integral of this model that I showed you reduces on a sphere to a matrix integral that is written on the slide. Well, not really fully written on the slide. Uh, the, the claim is that you localize the path integral to 2 points, the north pole and the south pole of the sphere. And then at those fixed points, one has to compute the action of Yang-Mills, which is very simple. It gives you this exponential Gaussian piece. Sigma is one of the scalar fields. So the only thing that can be excited while keeping supersymmetry is this scalar phi 0, which I've made dimension less by a factor of r here. So sigma is this adjoint scalar field phi 0. So sigma is a matrix, right? It's an n by n matrix. This sigma is the usual Haar measure on matrices. And then one has to study one loop determinants, and one gets some relatively standard infinite product formulas that I'm not presenting here. And so I have now a matrix integral with explicitly known integrand that I can use to compute the path integral on this Brown sphere. At large n, what you can do is to approximate this n by n matrix and its eigenvalues in terms of a continuous distribution, which I call rho of sigma. So now sigma is just some continuous variable that goes over the eigenvalues of the matrix. And then this kernel that I call G here, capital G, this is deduced from this one loop determinant. Okay? And what's important here is that I'm at large n. So first of all, it's only at large n that I can do this eigenvalue density distribution. Second, at large n, what I have not explicitly put here are instantons. So non-perturbative contributions, which are known in some sense, but they are at large n should be exponentially suppressed, so I will ignore them. And that's what actually simplifies the large n analysis. Okay? So now you have to find, you have to solve this integral equation, if you wish, and find rho of sigma, given this kernel. And as you see here, the dimension of space appears as a parameter, d. This equation is obtained for integer values of d, but once you have it for integer values of d, you can then analytically continue and have a nice formula like the one I'm writing here. Okay? So then you have to solve this equation through some saddle point analysis, which we've done, and you find the eigenvalue density written here. So this is valid now at large n and large lambda. So I have to assume large lambda for the saddle point. And then this parameter b is determined by just integrating this rho of sigma and imposing that integral of rho of sigma is equal to 1, right? Rho is a probability distribution. It has to be normalized appropriately to 1, and this is what fixes this parameter b. And you can see how explicitly here. And okay, that's all I need, right? So I've solved the matrix integral at large n and large lambda, and I can take minus log of that integral and call it the free energy. And this is the final answer. And I can reorganize the final answer as written here in red. So this CP is some explicit 2's and pi's and gamma, which you can get out of here. And then there's the funny power of lambda, and then there's n squared. Now, if you remember the first slide I showed you, I told you that from the supergravity side, we expect exactly this power of lambda and this n squared for the on-shell action. Now I've obtained this using the QFT side. So already the scaling that the QFT gives me at large n and large lambda is the correct scaling. But I can also compute now the coefficient in front. I know it's some boring 2's and pi's, but it's important because soon I'll try to convince you that I can compute exactly the same 2's and pi's from the bulk side, from the gravity side. And then I can also do something else. I can insert this Wilson line here in red on the equator of the sphere. The reason I'm choosing that specific loop operator is that that one is compatible with supersymmetry, and so I can again use the matrix model, but now with an insertion. And then using this eigenvalue distribution, again compute its expectation value. So this is again something compatible with the expectation from the scaling is compatible with the expectations from supergravity, and the coefficient is something that we now compute for the first time using the matrix model. Okay? Good. So that's all I'm going to tell you about the QFT side. Any questions about this? Okay, no. Just to
Nikolay,
wrap up,
just
I have
historical
yes,
question. When
yes, please.
when was this result obtained and finalized? I mean, I'm just curious.
These two in red were obtained in this paper with Joe Minahan, this one, 1910. So it's been 6 or 7 years already.
Mhm.
I mean, a part of the reason that we kind of stopped dealing with this is that no one cared. So if you're asking about the sociology of this, is that no one really cared about these things. And then Maldacena and Bix wrote a paper for Dp-branes, and they kind of cared a lot. And so then we got excited about it again and did other things. But yes, the things I'm showing you now are quite old. Okay, good. Well, all of this, as you saw, D is a parameter, but that the actual QFTs live in integer dimensions, so you can try to get explicit answers for integer values of D. And okay, except for D equals 1, everything else is kind of, you just put the value of D that you care about in the general formula. Interestingly, for Dp-branes, there's something like a singularity. So the free energy goes to 0. This epsilon is some small deviation from 1. The free energy goes to 0. The Wilson line blows up. We currently don't really have a good way to understand why this happens. Yes. Okay. Good. Now I move to the bulk side, and I'll try to show you how to construct the dual supergravity solutions. Okay. So if you
Sorry, Nikolay,
if you
can I
attack
ask you another
yes,
very naive
yes,
question?
yes, please.
I mean, so in dimension lower than 4, you would expect other models to arise, like Chern-Simons models and etc. Or they don't. I mean, in 3 dimension, if I remember correctly, for example, if you want to take the 3-dimensional Yang-Mills or 2-dimensional Yang-Mills, the localization, I mean, it's an exact term in the localization, correct? Or,
Very good. Very
so
good.
I just wonder which model are we really looking at holographically, because yeah.
Well, what I think what you're saying, I mean, what you're saying is exactly right. If someone tells you, I'm doing D2-branes, let's do 3D Yang-Mills or P equal to 2 in my conventions. So these are D2-branes. And of course, the expectation is that D2-branes on flat space, importantly, at low energies, very low energies, they should flow. So it's an asymptotically free theory. So as I go to low energies, it gets strongly coupled. And the expectation is that at super low energies, you generate a Chern-Simons term and you get ABGM, right? This is also expected from the type 2A string and M theory, right? As I go to lower energy, I get strongly coupled, the dilaton grows, an 11 dimension opens up, and I get M2-branes. That's the picture that everyone, well, I guess, which is why we are asking the question, right? But here I'm doing something slightly different. I'm first putting D2-branes or super Yang-Mills on a sphere. I'm keeping the radius of the sphere finite. So I'm excising the very low energy regime. So
Yeah,
if
okay.
you
So it's
wish,
because of the cutoff in the
exactly.
infrared. Okay.
Yes.
Yeah,
So
yeah.
in principle, you can worry, and we did worry about order of limits issues, right? In principle, if I now keep this R finite and then scale it to infinity, do I get ABGM or not? And I think this is a subtle limit. Yes. But if you keep the radius of the sphere finite, you should not expect to get the ABGM theory and the Chern-Simons terms because I cannot access the low energies.
Yeah, thank you.
Yes, that's the picture I had at least. Okay. And by the way, everything that I said, you will see explicitly on the dual supergravity side. So if you think that I'm full of like rough arguments and blah, blah words, we know. You'll see with equations how it works. Okay. So now the problem is conceptually easy. I have some D-branes with curved world volumes, these spherical D-branes. I have to backreact them and find the supergravity solution, right? And of course, naively, you should do this in type 2a or type 2b supergravity. However, if you look at the symmetries preserved by the problem, you will quickly get convinced that you would arrive at a PDE that you have to solve. So if you make an ansatz compatible with supersymmetry, you'll have to solve on partial differential equations. So to avoid this, we use the well-known trick, which is to appeal to a consistent truncation to a lower dimensional supergravity theory in p plus 2 dimensions. So for D2-branes, this will be 4D supergravity, let's say. And then try to find our solutions in that lower dimensional supergravity theory. This is along the lines of the usual tricks that people use in ADS, where they often, to construct explicit solutions, you go to some lower dimensional consistent truncation. So as an idea, this is not new. But here we have detailed control what we are turning on the QFT side. So on the QFT side, I have one operator, which is Jiang-Mills, which is just the Yang-Mills term, which couples to Jiang-Mills. So I should have one scalar for that in the bulk, and then two more scalars dual to this scalar bilinear phi in the QFT and fermionic bilinear psi in the QFT. These are schematically the forms of the two operators that I'm turning on by putting the theory on the sphere. In addition, I know that I have to break this R symmetry group to the following subgroup. And so I have orientation, what kind of a supergravity theory I should be looking for. I should have a maximal supersymmetry. I should have this big of a gauge group with the following symmetry breaking pattern, and then try to keep at least these three scalars. And so this was our job. And then we went to the Sugra literature from the 80s, which is not a very pleasant experience, I should say. And then out of the literature for these values of P, so as you see, some of the values of P are missing, but we find relevant supergravity theory with the gauge group that we need. And so the only thing we needed to do is to kind of weak rotate this to Euclidean signature, because of course in the old papers people cared about Lorentzian solutions, and what we want are Euclidean solutions. Okay, and then after this long song and dance, what happens is that the model is actually very simple. So I can show it to you on half a slide. What happens is that in each of these supergravity theories, there's a consistent truncation to three scalars. One scalar, which we call zeta, which you can think of as the lower dimensional manifestation of the type 2a or type 2b dilaton. So this zeta is, roughly speaking, the dilaton. And this tau and tau tilde is in Lorentzian signature a complex scalar where the real part is dual to this operator and the imaginary part is dual to this operator. Now I'm in Euclidean signature, so instead of a bar, I use a tilde to indicate that these two things are not necessarily complex conjugate. And then you have an explicit potential in this model, which is written in the usual way in terms of a superpotential W. And then the only thing that you have to kind of be careful about are some constants and some signs. And so what we found is that for p less than 3, you have to use the superpotential on the first line. For p more than 3, you have to use the superpotential on the second line. So my claim is that this model arises as a consistent truncation from all of these 5 supergravity theories. And by just looking at the explicit models, we could find a p-dependent formula. So now p can be viewed as a parameter. Interestingly, for p equals -1 and 1, we couldn't find a relevant paper. But for p minus 1, Samt, Leuven, and Ciceri, after our papers, they found what they call 1D supergravity. So p minus 1 is d minus 1 brane. So the supergravity theory should be 1D supergravity. Sounds exotic, but what they found is exactly a model that gives you on the nose everything I'm showing here. So this was after our work in kind of independently uncovered by them for p equals -1. So all of this is to say that we have confidence that we're doing the right thing here. Okay, so I've constructed the supergravity theory, but I want to do more now. I want to find solutions of this theory that keep all of the supercharges, right? So this is usually something that doesn't really happen so much, that you have a solution that has some flowing scalar fields and keeps all of the supercharges. So here it's not clear that this will work out, but in fact it does. So I'm making a very simple ansatz for the metric. So this is now this lower dimensional supergravity theory. You can think of this omega p plus 1 as the boundary sphere on which my quantum field theory lives. And this r is the radial direction. And then I have these 3 scalar fields and 1 metric function, and everything can be a function of this r direction. And then I have to go and analyze the Killing-Spinner equation of the supergravity theory. The SUSY variations have to vanish. And amazingly, imposing that all of them vanish, keeping 16 supercharges, gives you a unique system of ordinary differential equations written here in terms of the superpotential and the Kähler potential. And then you have to solve these nonlinear ODEs to find your solution of interest. I'm sparing you the details. I'm not going to show you. For some values of p, we have analytic expressions. For other values of p, we don't. But the picture is always the same. So the picture realizes what I tried to explain to Gabriele in words. So near the boundary of this space, so for very large values of the radial, the asymptotics, you asymptote to these known analytic simple Dp-brane solutions that I showed you on the first slide. And as you go into the bulk more and more, you feel the fact that your QFT is on a curved space, and you get a back reaction, and the solution changes and kind of smoothly caps off like this. So there's a cigar-like background that you find, which is completely smooth at the origin. So this cures, I mean, at the beginning of the talk, I told you that the solutions for these flat Dp-branes cannot be trusted at large r and small r. Now I have cured the small r naked singularity, if you wish. So this completely smooth here, and at large r, I have exactly the same asymptotics as before. Okay, is that clear? Okay. And importantly, once you impose the smoothness condition here, there's only one integration constant out of these three ODEs. So you have a one parameter family of solutions, which essentially the parameter can be thought of as controlling how long is this cigar or this kind of Hawking page type picture. Okay, so that parameter controls the length of this space. Okay, and just to show you that we're not full of crap, one can take the lower dimensional supergravity theory, the solutions we have constructed there, and explicitly uplift them to a solution of type 2a or type 2b supergravity. So this slide is just to show you, to calm you down if you're nervous, that these are actual type 2a and type 2b supergravity solutions. They're very messy. All of the fluxes, B2, Ramon fields, dilaton, everything is being turned on. But otherwise, we have explicit solutions. Okay? Any questions?
Yeah, just
These solutions are smooth in 10 dimensions.
Very good. So the picture, so here in the infrared, they're smooth in upstairs and also downstairs. So they're completely smooth in the IR. But in the UV, as I said at the beginning, you should always cut off the space-time, right?
Okay.
So as you go towards the UV, unlike in ADS, so in ADS, of course, if I have a picture like this would be a completely smooth solution. But here, as you go to larger and larger values of R, the dilaton blows up. Okay? And so at some point, you should stop trusting the supergravity approximation. Yes.
And when you compute on-shell action, do you need to add counter terms, so on?
I will try to explain this now.
Okay.
So you are two minutes too early with your question. Indeed, you should worry. How do you compute? Now I have a smooth thing in the IR, so I've cured a part of the problem. Right? I mean, at very early in the talk, I told you that people have studied the Schwarzschild solution in this background, and indeed, it kind of does the same thing. It cuts off the IR, but now with a black hole horizon and finite value of the temperature and broken supersymmetry. So all I've done here is to do the same, but not having a black hole, having a big sphere that goes to zero size in a smooth way. But I still have to address this infinity issue here, as you ask.
Sorry, can I ask a question?
Yes, please.
The consistent truncations are still on spheres.
I'm not sure I understand. The internal space is a sphere.
Yes, exactly.
Is what you're asking?
Yeah.
Well, if you really want to be annoying, good. We choose funny reality conditions for spinors. So this leads. So this is the internal space you're asking me. Okay.
Yeah.
So if you want to close your eyes, you can call this a squashing of the sphere. Like if you put P equals 1 and Q equals 1, you're just going to get an internal sphere.
Yeah.
But P and Q are something which is a function of the scalar fields. So this X and Y are the scalar fields tau and tau bar. And so as you flow, the sphere is being squashed.
Okay.
However, we work in conventions where this chunk of the space, this omega-2, is actually de Sitter space. So this is a Lorentzian solution in type. So we wanted to avoid to talk about type 2 supergravity in purely Euclidean signature. And so the red piece, as I told you many times, is Euclidean entirely. And so for that reason, we analytically continued a part of the internal space.
All right. Okay. So the Lorentzian direction is in what you would call the internal space.
Yeah, this has to do with what I told you here, right? That the gauge group of the supergravity theory is non-compact. I'm choosing these weird conventions, right?
Okay. So topologically, this is not whatever you're considering here times some sphere or some product, it's something more complicated in the internal space.
I would say no. Maybe this is a red herring. So take this thing that I called the Sitter space and make it into an S2 by analytic
Okay.
continuation.
Okay. Okay.
What's
Yeah.
going to happen is that this B field, so this B2 field is the volume form of exactly that space.
Yeah.
This thing is going to get an I. So you will find a nice solution in Euclidean signature for the metric, but then with imaginary flux.
Yes. Okay.
Something has
Thank
to
you.
give at some point. I'm doing Euclidean supersymmetry, so these things are strangely complex, right?
Yeah. Okay. Thank you. Yeah.
Yeah. But otherwise, this looks just like if you want to do ADS5S5 and want to study some RG flow, holographic domain wall. What's going to happen on the internal S5 is exactly this kind of a squashing with a P and a Q function.
Yeah.
Okay. So in that sense, I'm not doing anything different.
Yes. Thank you.
Okay. Yeah. Good. All right. How am I doing on time, by the way? Robert, do I have 10 minutes or so?
Yeah, you can do 10 minutes.
Okay. Thank you. Good. So now, quickly, very early in the talk, I told you about lambda QFT, the Toft coupling. And now the notation finally will make sense because I need to find the holographic dictionary. And in usual ADS5S5 and n equals 4, this is not ambiguous because Jiang Mills is just the dilaton, n is the number of Dp-branes, I'm done. But here I have Jiang Mills' dimension full, and so I need to introduce an energy scale to define a dimension less lambda. And in principle, you have a choice in how to choose that scale. So on the QFT side, I chose the energy scale to be 1 over the radius of the sphere. And I would like to make the same choice in the bulk. So for Jiang Mills, what we did is to just define Jiang Mills in the obvious open string way. G square Jiang Mills is e to the power of the dilaton, and the powers of 2 pi and ls are exactly the ones that you get from flat space. So the first identification is what you would naively do using open strings. But this one is a bit more funny. So I define the holographic size of the sphere, right? It is the size of the sphere, but the sphere changes as I go into the bulk solution. And so this R whole is actually a function of the radial variable in this Sugra background.
Oh, hi,
Yes.
Nikolay, I have a question. When you see the size of the sphere, you refer to a metric, and metric is in string frame or Einstein frame?
I carefully
Oh, sorry,
took
string
the
frame. I
words, but
didn't
of
say
course
it.
you have not read it. Yes. So if you wish, I take exactly the prefactor here,
Okay.
combined with
All
the
right.
e to the a, which is inside of the red bit, and I call that whole thing the size of the sphere.
All right. All right.
Okay. You may disagree with this or agree with this. I will try to convince you that if you want to make a different choice, it will not matter for the physics. But okay, this is what we did.
Mhm.
And then, amusingly, combining these ingredients, so n is n. N is always the number of Dp-branes. That's unambiguously computed by flux quantization. And then I combine these things in the formula above, and I take the limit r going to infinity, and I find a finite object for all p. And this is what I call a lambda holographic. Okay? Good. But I'm not yet done. As E asked me, I have to compute a non-shell action. And this is actually very subtle. I have infinities. But you have infinities in anti-de Sitter also, right? Those infinities are, however, well understood. Pfefferman-Graham expansion, counter terms, and so on. So we need to learn how to cancel infinities in these weird asymptotically linear dilaton backgrounds. Luckily, Skenderis and friends have told us how to do this. So that they have a proposal which, frankly speaking, when you see it for the first time, it appears to be pulled out of a hat. But okay, that's what they argue one should do, and we did exactly that. And I'll show you that it's a winning strategy. But I want to warn you that this is on a much less rigorous footing than the Pfefferman-Graham expansion. I mean, Pfefferman and Graham are mathematicians, so they carefully studied conformal boundaries in anti de Sitter, carefully defined things, and so on. This is trying to mimic that with more of a physics attitude, if you wish. So the observation of Skenderis, Marika Taylor, and others is that you can take the metric that I showed you, this lower dimensional gauge supergravity metric, and rescale to a conformal frame, which they call dual frame. Okay? This frame is not string frame, and it's not Einstein frame. It's defined in such a way that the new metric G tilde is exactly anti de Sitter space. And this is a little bit of a miracle that the dilaton, so this zeta, as I told you, is the dilaton field. The dilaton has a radial dependence that compensates, if you wish, the radial dependence of the metric. And when you combine them with the right power, a little a here, you'll get exactly this anti de Sitter space. So now the metric is anti de Sitter, but the dilaton still runs. Right? This you cannot kill. And of course, this is possible because now your action is not in Einstein frame. There's this factor in red here that you have to keep track of. And so the claim of Skenderis et al. Is that you should take this action here with the factor in red and do the usual counter terms for anti de Sitter now for everything that is inside of the curly brackets. So that's the algorithm that they proposed. And we actually followed that. And I'm sparing you maybe 20, 30 pages of explicit results and calculations. But when you do this, amazingly, everything just works. So you find that the regularized on-shell action, which gives you the free energy of the supergravity solution, is exactly identical to this matrix model free energy that I showed you. So F is equal to F, which is the logarithmic version of Z is equal to Z that I started with. Okay, we can do a bit more. We can compute another observable in the bulk, which corresponds to this Wilson line that I told you. Here, things are somehow nicer. What you have to compute is the expectation value of a fundamental string. So you first have to find the minimal of the Nambu go-to action. So I have a Nambu go-to action and a B field, or Polakov action, whatever you want to call it. And you want to find where does the string want to sit. And you find that it wants to sit on the great circle of the boundary sphere and then some very special internal points. And then once you've solved for the configuration of the string, you have to compute the on-shell action of that string. It of course diverges again, but this time there's a unique counter term that you can add. You don't have to think too much. There's only one way to cancel this infinity, and whatever is left over is just agreeing again on the nose with the matrix model. So now I've computed two things on the matrix model side, computed two things on the boundary side after a long song and dance. And so hopefully this is somewhat convincing that something like holography should work in this kind of setup. Okay, so in the remaining 2 minutes, I will try to very briefly tell you how to compute Witten diagrams. Okay, so far I've computed, so if you think about it, I haven't done much. I've computed a 0-point function, meaning the free energy, no insertions, and the expectation value of a Wilson line, so a non-local operator. You may want to be more ambitious and compute correlators. 2-point functions, maybe 3-point functions, maybe 4-point functions. How do we do this? It's not immediately obvious. So now I will go back to the flat branes. So forget about these spherical branes, these extra scalars, these weird flows, and so on. I have the simple solutions that I started with, and I have written them here in this lower dimensional supergravity theory, directly in this dual frame that I told you about. So now I have only one lower dimensional scalar, the dilaton, phi. And in this dual frame, the action is very simple. It looks like Einstein-Hilbert plus a cosmological constant plus a kinetic term for a massless scalar field, but all of this is in some funny conformal frame. And the solution is, as I told you, the metric is anti-de Sitter space, and the dilaton is a very simple, so e to the phi is some polynomial of z. Okay? And early on, I told you that there's this thing called a scaling similarity. So indeed, it's almost immediate to see that if you shift phi to phi plus a constant, the equations of motion are invariant, but the action is not invariant. The action gets multiplied by a constant term because of this weird conformal frame. So that's why it is not called a symmetry, but a similarity. And of course, when d is equal to 4, when we have Dp-branes, then this is really a symmetry. This is the scaling symmetry of ADS5S5. Okay, so now I want to do scattering amplitudes in this background, meaning correlation functions. And so now I take a scalar field chi, just a probe scalar field of mass m, and I want to compute its propagator and its interaction vertices. In other words, I want to compute Witten diagrams in this background. And what you find is that things look almost like in anti-de Sitter space, except with some minor modifications. So this mass of the scalar can be identified with a dimension of a dual operator, even though I don't have a CFT. I have some scaling covariance. And this eta is some fractional number in terms of the dimension. So this this delta is the dimension of the operator dual to chi. And then you can go ahead and try to do ADS CFT just like in the books. And what you find is amusingly simple, at least looks very simple. So everything that you see on the left side are the anti-de Sitter answers that you find from the books. And everything that is on the on the right-hand side in red is this scaling covariant background that I just showed you. So the bulk to boundary propagator is given here in ADS, and it gets slightly modified by this eta power. Z is the radial of ADS. The bulk to bulk propagator is this hypergeometric in ADS. It's again a hypergeometric up to a prefactor in this scaling similar background. And then if you have an interaction in the bulk, if you have not just a 2-point function, but a higher point function, the integral that you have to do for the interaction vertex in ADS is just this invariant volume. And here it is modified again by this eta. So now you have rules for scattering a la Witten, and you can just write down any scattering amplitude in this background, at least as an integral. What you find immediately is the 2-point function. It's just this propagator, bulk to boundary, but now boundary to boundary. And you find a polynomial fall off. So the 2-point functions in this eta modified story just look like a CFT 2-point function with some slightly modified powers. And so at this point, you may be inclined to say, oh, it's just going to be some modification of conformal dimensions, and otherwise I'm going to find the usual ADS answers. But when you compute a 3-point function, you find the following gory mess, which is here.
Hi, Nikolay.
Yes.
What is the unitarity bound for the delta, the scaling dimension here?
Very good.
In this setup.
Yeah, it's the usual one. So one way to think of this is that you have anti-de Sitter space in d plus eta dimensions. So
Okay.
if you combine d and eta, and then you just get the unitarity bound in d plus eta dimensions,
All right.
or the BF bound if you wish.
Mhm.
Yes, good point. So now the 3-point functions, and I'm done. I just want to show you that this is not a polynomial in the distance. This f4 is some kind of a Pell function, some fancy hypergeometric function. And so we were able to explicitly compute the integral, the Witten diagram, and it's a big mess. So this is not a CFT, but still has some interesting explicitly computable 3-point functions. They're computed from the bulk. And if you don't like a messy formula, we can get a nice plot. So this is a plot where I fix the conformal dimensions for some KK modes on the sphere. And then, okay, we chose the lowest KK mode and explicitly, so this is an explicit plot of this function here. And the A and the B are these are distances between the points. I have X, Y, and Z, the 3 points, and then out of them I can form 2 scale invariant ratios of the distances. And this is how I'm making a plot of a 3-point function. Okay? And so the claim is that from the bulk we have computed these 3-point functions in flat space for the super Yang-Mills theory. And of course, it would be nice to compute them from Yang-Mills, but I don't know how to do it. Okay, final comments. All of this is just an illustration for scalars. We also know how to do this for operators with spin. And so combining all of this thing, we have rules how to compute any endpoint function in the supergravity approximation using any of the Kaluza-Klein modes on the internal sphere, just like you would do in ADS5S5. We have the rules, but it doesn't mean that we know how to do these integrals. They're very, very complicated, but they're also very complicated in ADS5S5. You also need some spectroscopy here. If you want details, you need to find the masses of these operators explicitly, and so on and so forth. So some of these things we have done, and some of them still need to be fully done. And I want to emphasize that the structure I showed you is only for BPS operators. So for Kaluza-Klein supergravity excitations, if you study non-BPS operators, Maldacena and Bix have an argument that they will not have a power law 2-point function. It will be an exponential fall-off. Okay, I'm done. I told you how to do Dp-brane holography. Try to convince you that some things we can compute explicitly on the QFT side with SUSY localization and how to match them in the bulk. But these things are kind of boring observables. They're the free energy on the empty sphere or a Wilson line. Then we moved on and studied how to do more interesting observables like 2-point and 3-point functions in the bulk. And of course, there's many things to do. You can try to squash the sphere or add mass terms, study more interesting observables. They still should be computable with SUSY localization, but no one has really done it. You can ask about manifolds that are not spheres, like Gabriele asked me, I think, about the index. This has also not been studied. How much of this is leading order supergravity magic and how much survives 1 over n or 1 over lambda, I don't know. And in general, as I said, we told you what the rules are for these Witten diagrams, but it would be nice to also try to explicitly compute some of those and see what the structure is, and maybe we're going to learn something. And maybe our lattice friends will go to their computers and try to compute these 2-point and 3-point functions and see if they can agree with our answers. That's all I had to say. Thank you, and sorry for going over time.
You, I guess, question?
Okay. Hi, Nikolay. I have some naive question.
Please.
For Yang-Mills theory in flat space, the vacuum is not unique. They are separated by domain walls. Now, if we put a super Yang-Mills on on sphere and you cap off the IR region, I wonder if the vacuum become unique in this case.
Very good question. Very good question. So first of all, you are saying things a bit quickly. The vacuum is not unique, but there's a unique vacuum that keeps all of the R symmetry,
Okay.
right? If
Oh
you
yeah.
there is this, of course, I have Coulomb branch vacua. I can separate the branes as I wish, and I'm going to keep all of the 16 supercharges. But as I do this, the SO, let's do D2-branes, right? I have SO7 R symmetry.
Mm-hmm.
That SO7 is going to be broken by the VEFs, right?
Mm-hmm.
So yes, on a sphere, if you wish, I'm choosing first, I go to the origin of the vacuum moduli space, and then I put that on the sphere.
Mm-hmm.
But yes, indeed, these other vacuos are, if you wish, lifted. Other vacua are lifted by the sphere, right? When I put things on the sphere, I add energy.
Yeah.
So yeah. Also, it is a bit weird, right? On the sphere, I don't really have a Hamiltonian. So speaking of a vacuum now becomes strange a little bit, right?
Mm-hmm.
In,
Mm-hmm.
in Koski space, I can do the usual quantization. I can define P0, the eigenvalue of P0 is the energy, and so on and so forth. But here, the SUSY algebra doesn't naturally allow for the notion of energy.
But you can still you have this scaling dimension. Maybe one can use that generator.
Yeah, but this is a very funny thing. This scaling dimension is not a
Yeah,
property of the theory.
I see.
As I try to emphasize here, so it looks like I have 2-point functions that are scale covariant,
Mm-hmm.
but now this operator O is a half BPS operator.
Mm-hmm.
If you now study non-BPS operators, for instance, operators that are not dual to supergravity modes, but dual to strings, short strings,
Yeah.
those operators will have a 2-point function that is an exponential fall-off. So they will not have a scaling dimension.
Mm-hmm.
So it's some interesting structure that somehow the supergravity modes organize into something that has a notion of a scaling eigenvalue or energy, as you want to call it, but not all operators have it.
Oh, I see. Okay.
Yeah, yeah.
So, Nikolay, how much is known about various correlation functions on the sphere?
On the
If
sphere,
you want to
nothing is
compute
known
it.
about correlation functions.
Okay.
Well, okay. I should
Because
maybe
some technology has started to be done. I
yeah.
mean,
Sorry,
done
I should
for example, for correlation functions in ADS and etc. I mean, you could
yes.
try to analytically continue them and have
Yes.
something.
So, first of all, I want to say maybe this didn't come out. I was a bit hurrying at the end. Everything I told you about the correlators is for the theory on flat space. So I changed gears, right? From the first part of the talk was about the sphere, because then I wanted to compare with SUSY localization. But now the last few minutes were about flat space. Now, there's been attempts by Joe Minahan and friends, including a paper that came out last week, I think, to compute correlators with SUSY localization on the sphere. Now, I think at the moment, the situation is not, well, at least I don't know how to make a connection with this thing that I spoke about today. In principle, one can try. And in ADS, there had been successful stories. But yeah, at the moment, I don't know. The thing that I'm more optimistic about is this thing that I had on the to-do list. the first bullet point. So if you allow me to squash the sphere or add a mass term and break supersymmetry. So if I go to the first part of the talk and compute the free energy as a function of some squashing parameter. Because now the free energy I computed is just a number, right? It's the coupling to a power times n squared and then 2's and pi's in front. It's not a very interesting observable. But if you squash the sphere, I will have a function of the squashing. And then if you think about what the squashing does is that it turns on the energy momentum tensor. So if I expand in the squashing, for small values of the squashing, I'll get integrated correlators of the energy momentum tensor. And so this thing should be computable, and maybe using that, we can make connections with the correlators that I talked about. But this certainly has not been done. Yeah.
Yeah, I don't know. I will have other questions, but maybe we should let Nikolay go. It's 10:20.
No, I mean, if you
Maybe
want to ask,
maybe another very naive question. I mean,
Yeah,
there's a lot
please.
of supergravity generating solution techniques that has been used a lot. You might think, okay, what if I try to get some deformations of the supergravity solution that have? Can you apply them in some sense here? I don't know, the beta deformation or other type of deformations that you would use to
Yeah,
generate solutions, or yes?
I think if
To just
the
understand
goal
how
is
much you can deform the whole story, right?
yeah, so if we go back, my understanding, I mean, this paper that I started with, sorry, early on. So these backgrounds, the ones of Itzhaki, actually they were first written down in the early 90s by Horowitz and Strominger, but anyway. These are so simple that people have tried various generalizations here, right? As you say, I have a whole sphere here. I can try to do some solution generating techniques, make this, try to study these Coulomb branch flows that E asked about, separating the branes, mirroring the branes in some way and so on. So these things, and I don't know the full literature on this, but all of them suffer from the problem that I was emphasizing here, right? Yes, you will find some supergravity solution, which will generalize what you see on the slide, but what you see on the slide is already problematic, right? It has an infrared singularity and it has a UV singularity. So anything that you try to compute with it, so yes, you will find solutions, but what do you compute with them? How do you know that they're good physical solutions? What are they dual to? All of this is kind of murky, right? Whereas in ADS, all of these things that you asked about have been applied to ADS. And then once you get an ADS, it's fine, right? Because ADS is a nice space. You may not really understand the details of what you've done in the dual CFT, but still you have a nice background of supergravity. Whereas here, these are singular backgrounds and okay. Yeah, I don't know what to say.
Okay.
Yeah,
Hi, Nikolay. Can I ask a question?
please.
I was curious if you could explain a little bit more about the supersymmetry algebra on the sphere.
Okay, very good. I don't have slides on this, but let me try to improvise. So the general statement, and actually you could have asked me already here, why do you stop at d equals to 7? I mean, there's maximally supersymmetric Young-Mills. in dimensions 8, 9, and 10, right?
Mm.
You could have asked me, why don't I put 10-dimensional super Yang-Mills on S10, right?
Yep.
And the answer is very simple, and this was understood by Blau. There's no SUSY algebra, right? And the number 7 here is the same number, you should think of this as 6 plus 1. So the num classification of SUSY superconformal algebras stops at dimension 6.
Yeah, 60 to 0. So is that where the
Exactly.
7 comes from?
Yes, exactly. That's where the 7 comes from.
So where is the superconformal coming into the sphere from?
I mean, if you think of it as superconformal, you'll get infinitely confused, right? You don't have superconformal symmetry of the theory.
Mm.
You just use the superconformal algebra, right? So now let's think about an example. I'm telling you, let's do d equals to what do you want to do? Let's do d equals to 3, okay? So then you get something that has the isometries of S3,
Hmm.
right? It has SU2. Let's not worry about this being non-compact. So you have SO3, SO4, right?
Hmm.
SU2 and SO4. Okay? And
Ah,
this is
okay.
some when you combine it, this becomes some OSP whatever. OSP 4 slash something.
Is there a reason you wanted to land in a simple superalgebra? Because that's one of the key properties of these superconformal algebras.
My understanding is that you don't you don't have options basically. The only option you have is about certain signs.
Mm.
So what I told you about is about the theory on SD. You can ask about what about the theory on anti-de Sitter D, right? I can put this Yang-Mills on anti-de Sitter or on hyperbolic space if you wish, Euclidean hyperbolic space, and then I get the same, almost the same looking action with some signs different. And this was understood by Blau. The, the real thing that constrains this action, as far as I understand, is you insisting all the time to have 16 supercharges,
Ah, okay.
right? So if you want less SUSY, then the classification becomes more complicated.
Ah, okay. No, I think that makes sense to me now. Because you have to, represent that in the superalgebra, and that restricts
Exactly.
your
Yeah. There's
choices.
not many. Yeah. So another way of asking this is that you want to have a superalgebra that has a very large bosonic subalgebra, right?
Mm.
And 16 supercharges. And there's not many of these things around, right? And
Yeah.
it has to close,
Hmm.
right? So yes, we can call it superconformal because that's how it was found. But if you it is just a superalgebra that has a lot of fermionic generators and a lot of bosonic generators.
Yeah, yeah, sure. Thank you.
Yeah. All right. I guess it's pretty late for you guys, so I should leave you alone, huh?